Okay, you should have been able to get this because what we see here is a slope of 1/2 with a run that's equal to the 0.013, which is our change in y. So it's slope of the y function at the corresponding point, slope of the f of xy function confined to the plane x equals 0.71 or square root of 2 over 2. It's the slope of that graph times that increment 0.013, and that 0.013 increment, remember, came from the 0.02 change in the value of t run through the natural log function estimated by differential here. Okay. And that result is just then run times slope equals rise. So the rise is 0.013 times slope 1/2. Run 0.013 times slope 1/2, or about 0.065. Now, this 0.013, remember, was calculated, as I indicated a minute ago, by a differential approximation, y prime of t times delta t. Just the slope of your y versus t graph multiplied by delta t. The change here, the rise, is equal to the run, which is negative 0.014, multiplied by the slope, square root of 2 over 2, approximated by 0.707. Well, if we multiply these out, and if we use the exact values, in fact, we get exactly negative 0.01. And again, we can make the note that x prime of t delta t, that's our negative 0.014. That's the change in x that's dictated by this change of 0.02 in y. And then we multiply that by the slope of the function in the x direction. Now that function is the partial of f, well, the slope is given by partial of f with respect to x evaluated at the xy point, 0.71, 0.69. And the slope here, the 0.1/2, is calculated by the partial of f with respect to y at this point. And let's just be careful, let's be sure partial of f with respect to y is what? It's x squared y. Okay, our function x squared y, I'm just checking. Okay, can you see around me? Okay, x squared y. Partial of that with respect to y, well, we're confining ourselves to just this function. And the derivative of this function then with respect to y is just x squared. Okay. If we value that, weight that for x equals 0.71, which represents square root of 2 over 2, we do get our 1/2, don't we? And the partial of f, so the partial of f with respect to y at 0.71, 0.69 is approximately 0.71 squared, which is approximately 1/2. And it turns out that it really is 1/2 if we use the square root of 2 over 2 for the x coordinate. Okay, and over here, partial of f with respect to y. And we want the partial of f with respect to x. I'm not sure why I wrote y there. Partial of f with respect to x. Treat y as a constant, take the derivative with respect to x. Everybody understands this. That gives us 2xy. And if we multiply this x by this y and by 2, we get a slope very close to 0.707. So, there's our result for the change as we move in this direction. Okay, the change is negative 0.01. And the change as we move in this direction, that change being 0.065. So the net change is, if we move from here to here, well, we move from here to here, we go down 0.01. if we move from here to here, we expect that we go up by very nearly the same amount we go up by here, and that would be 0.065, and that would give us a net change of negative 0.01 plus 0.065, which is then negative 0.035. Now, let's just kind of summarize what this tells us. Okay, our change in Z, which is our change in F, is equal to what? Well, it's equal using these expressions. This is your partial of F with respect to X, evaluated, of course, at the appropriate point, multiplied by X prime of T delta T. Well, instead of X prime of T, I'm going to write dx dt times delta T. And then, so we see a chain. Partial F with respect to X, derivative of X with respect to T gives us partial of F with respect to T, or in this case the derivative of F with respect to T, and we won't worry about that distinction right now. Okay, and similarly, this expression, our y prime of T delta T times partial of F with respect to Y and so forth, we just rearrange that. There's partial with respect to Y, and there's, instead of Y prime dy, we use dy dt times delta T. And that's what we added here numerically in terms of this picture. Then, since this is what our delta F is equal to, and I should say it's approximately equal, our delta F over delta T then will be approximately equal to, well, what we get when we divide out the delta T from each of these terms. Partial of F with respect to X times dx dt plus a partial of F with respect to Y times dy dt. As we take the limit, if we take the limit as delta T goes to 0, the approximation becomes exact, and we say that then, don't have room to write it, but we would write, well, I'll try, df dt equals, and I'll just write etc. df dt equals doesn't approximately equal, it equals this expression. And there's our chain rule. Now, to really deeply understand this, it's important to understand what's going on again. Just to review it once more. A small change in t results in some small change in x in this picture. So small change in t here gives us a small change in x. It's a negative change, and it goes here in our three-dimensional diagram. Our small change in t gives us a change in y, which is a positive change. So that's going to be a positive change in y. And then, according to the derivatives of this function in x, y, z space, or in the xy plane actually, we see what the slopes are here and here. So we can use this run with this slope to find out what contribution the y motion makes. And then we use this run, the negative 0.014, to see what kind of change the x motion makes, giving us a net change when we get around to this point. It's the sum of the changes we get from here and here. And right here are all the relevant quantities. Okay? So, that's the meaning of the partial derivative. And that's an illustration of the meaning.